Alright, so this should be your first video for our Math 142 class. All the videos for our class will kind of work the same way. I'll open up the video and I'll have a kind of a typed up sheet that I spent countless hours writing and rewriting to make them perfect in my mind, that talk about some of the concepts in Math 142. And then after I've done enough concepts that we have enough knowledge to do some problems, I will do some problems. And very specifically, every section has, I don't know, a bunch of problems, 20, 30, 40 problems. And I will, as I go through my lectures, I will do every single even numbered problem in the section that I'm lecturing on, with the idea that the lecture that I give and the problem that I solve will motivate you to be able to solve your homework problem. In every section, the homework you're supposed to do is all the odd numbered problems. So eventually I'll get to the very first two homework problems in section 1.1. I'll do problem 2. After I do problem 2, I'd like you to pause the video and try to do problem 1. At the very end of the section, there are answers to every single odd numbered problem, so you should be able to check your answer to make sure it's right. Once you have an answer that's correct, then you can move on and just keep watching the video. You don't technically have to watch every minute of every video. You'd probably go crazy if you actually did. I spend a long time talking, probably a bit too long. And if you feel comfortable with the concept, comfortable enough that you can fast forward and do the problems that concept, is that I'm lecturing on, feel free to skip through chunks of the videos if you can. Some students don't even watch the videos, they just read what I've written and they're able to do the problems from that. And heck, that's impressive. If you can do that, that's more power to you. So let me just start, and I'll go through my write-up, which you could read. I'll probably try to add a little bit of more detail as I read through this stuff. So the first section's on a concept called sets. This was a big concept in the 70s when I went to grade school. When I went to grade school, we studied sets in every math class, every grade. Starting in first grade, I started studying sets. That's not the case so much anymore, so some of the concepts that we're going to get in here, although they're simple, there's maybe things that you haven't seen before. So the first word I have is set, and I define set as a collection of objects. And that's a pretty vague definition. An example of a set might be the set of cars that I've owned. Or maybe another example of a set might be the set of students enrolled in our class. So a set is just a collection of objects, and these objects are usually called elements or members. For me, some of the elements in the sets of cars that I owned, my first car was a 1966 VW, and then I had a 1970 Mustang. So those cars, the 66 Volkswagen and the 70 Mustang, those are elements in the sets of cars that I owned, or the members of the set of cars that I've owned. I don't have our roster in front of us, so I couldn't give a name of any student in the class right now. It's going to change from semester to semester anyways. So a set's just a collection of objects. The objects are often called elements or members, and sets are usually given capital letter names. So if I wanted to name the set of cars that I've owned, maybe I'll call it C equal to set of cars that I own and give it a capital letter name. And I don't know, N equal to the set of students enrolled in this class, maybe N standing for name. This example is supposed to help us understand the concept of a set, maybe kind of how we're going to use it in this class a little bit. So I wrote an example. I said, let A be the set of integers between 2 and 5 inclusive. List the elements of set A and place the elements in set braces. There are a bunch of things going on here. First of all, I have to understand what I'm describing is a set, and it's really, really easy to become a set. This question wouldn't make sense to ask unless A was a set, and the bar is really set quite low to be a set. To be a set, you just need to be a collection of objects, and this set's a collection of integers between 2 and 5 inclusive. It's a collection of objects. In this case, the objects are the integers, or the numbers in the set. There's no requirement on what these elements can be. The elements or objects in the sets can be numbers, students, cars. They can be anything. There's no requirement on what the elements have to be. As long as the set is a collection of objects, then it's going to be a set. If I read through my example, there are a couple words bolded in the description, the words integers and inclusive. And in order to come up with an answer to list all the elements of set A and place them in set braces, I really need to know what those two words mean. And on the next page, I told myself, well, these are what I want integers to be. Integers are essentially numbers without decimals, whether positive or negative. Integers are like -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5. These dots means the pattern continues. So the integers don't stop. They go on forever in both directions. Any negative number without a decimal that you can think is going to be an integer. Any positive number that's not a fraction or a decimal is going to be an integer. So when I'm asked to list the elements of set A, I need to understand the kinds of numbers, and these are numbers without decimals, without fractions. I also need to understand the word inclusive. When you're asked to list numbers between in our class, you almost always have the word inclusive or exclusive after the word between. So when it asks me to list integers, I know that I'm looking for these kinds of numbers. Between 2 and 5 isn't enough for our class. After between 2 and 5, we need to put the word inclusive or exclusive. If I use the word inclusive, it means to include the first and the last number. So our set A is going to include the 2 and the 5. If this word inclusive was changed to exclusive, then I'd only include the numbers between 2 and 5 and without including the 2 and the 5. So let me try to make a stab at doing this now that I kind of understand the words. The set is called A. Usually when I'm writing down the members or elements of a set, I write the set name, then I follow it by an equal sign, and the instructions here said list the elements in set braces. Set braces are kind of curly braces that look like this. I don't forget exactly where they are on my calculator. On my calculator, on my computer, there's a button for this. Inside these set braces, I need to list the elements of set A. Super easy. From this list right here, I could just see all the elements. Those are the integers between 2 and 5, including the 2 and 5. If it said exclusive, the elements would be 3 and 4, but the elements of our set A is going to be the numbers 2, 3, 4, and 5. And that's all there is to do for this example. I've listed all the elements of the set. I named the set with a capital letter that I was told to name it with. I put the elements in set braces, and I only put integers between 2 and 5. I included the 2 and 5. I did everything I needed to do for that problem. The words that are here, either I've talked about or I don't have more to say. I think I've talked about them well enough. All right. And then as I go through here, I talked about the words integers, inclusive, talked about this is all just what I said. One thing I didn't mention, when I'm asked you to write set A, when I wrote set A down, I instinctively wrote this set A with the numbers going from smallest to largest. It turns out that it would have been equally okay if I wrote the numbers from biggest to smallest. These set braces get really bad by me because I'm not that good at drawing them. Or I could have written the numbers in some odd order. As long as the set had the elements 2, 3, 4, and 5, the order that I wrote the elements in aren't important. And that's kind of what this says here. The order that the elements of the set A are listed in is not important. It has no effect on the set itself. The set A described above can have its elements listed in many ways, and there's 24 different ways I could actually list those elements. And then I've already hinted at this. Had my examples used the word exclusive as opposed to inclusive, the 2 and the 5 wouldn't be included in the set. So let me do this next example. Let A be the set of integers between 2 and 5 exclusive. List the elements of set A and put them in set braces. So usually when I'm asked to list the elements of a set, I know the name of the set. The name's usually a capital letter. I write that name down, followed by an equal sign. Then I put set braces, and inside those set braces I put the elements of the set. And again, integers between 2 and 5, at most they're the numbers 2, 3, 4, and 5. But if after the description of the numbers I see the word exclusive, you don't include the numbers that are mentioned, you only include the numbers between, but not the numbers themselves. So the numbers that are going to go in set A are just the numbers 3 and 4. Apparently I have another example that's going to help us when we get into the homework. So let B be the set of solutions to the problem x plus 5 equal to 8. List the elements of B and place them in set braces. So I know when I go to answer this, I'm listing the elements of a set. Usually I name the set, I put an equal sign, and then after that equal sign I put squiggly braces, and inside the squiggly braces I put the elements of the set. Well, the elements of the set are the solutions to this equation, and in order to get the elements that belong in the set, I have to solve this equation. And so it's super easy to solve this equation. I don't think we're going to do anything much more complicated than this in terms of algebra in our class. There's no factoring in our class. So to get the elements of the sets, I just need to solve this equation for x by minusing 5 from both sides. And when I get this equation solved, I only get one answer, 3. So 3 is the only solution to this set. 3 is the only number that's going to go in the set braces for my answer. So the answer is going to be B, is the set that contains the number 3. Finally, going to get to some homework problems. So question 1 is your homework problem. Mine is question 2. So I'm going to try to do question 2. So I'm supposed to list all the elements of the set and write my answer including in set braces. For question 2, the name of the set is A. So I'm going to write the name of my set A. I'm going to put a squiggly bracket. And then inside the squiggly bracket, I'm going to put the numbers that are in the set. And my set is odd numbers between 1 and 10 inclusive. Well, odd numbers are 1, 3, 5, 7, 9, 11, 13. I'm supposed to put the odd numbers that are between 1 and 10, so I definitely wouldn't want 11 and 13 because those are bigger than 10. And inclusive means include the 1 and include the 10 in your answer. When I go to write my answer, I'm definitely going to include my 1 because 1 is an odd number between 1 and 10, and I'm asked to include the n numbers if they're part of the set. But I'm not going to put 10 in my answer. I only include the last number and the first number if they're part of the set. And because 10's not an odd number, it doesn't belong in my set. So I'm going to write just 1, 3, 5, 7, and 9 for my answer to question 2. When you go to do question 1, you should do something really similarly, except you're going to be dealing with the even numbers between 1 and 10, and even numbers like 2, 4, 6, 8, and 10. You have to decide which numbers belong in the set and which numbers don't. When you get your answer, you should check it at the back of the last part of this section to see that it's right. Let me move on to do 3 and 4. Again, you can pause the video, do 3, and not even watch me do 4 if you feel you know how to do these problems already. So for my problem 4, set B, I'm going to write B equals, and then I'm going to write the set braces. And then inside my set needs to be odd numbers between 1 and 10 exclusive. Here's all the odd numbers between 1 and 10. And exclusive means don't include the first nor the last number. So I couldn't include the 1. I can't include the 10. I'm not going to include the 10 naturally because it's not an odd number. I'm also not going to include the 1 because of the word exclusive. My answer to problem 4 is going to be 3, 5, 7, and 9. So you should give problem 3 a go, and hopefully I have the right answer there. So we get 5 and 6 to do here. Let me work on 6. 6, the set A, so I'm going to write A followed by an equal sign, put my squiggly brackets, and A has a set of solutions to x minus 4 equals to 9, so I need to do the algebra to solve this. The algebra that I'm going to do is I'm going to add 4 to both sides, and that's going to give me x equal to 13. This equation only has one solution, so the only element in set A is the number 13. A 7 and 8 aren't the kinds of questions I would ask on a test because I might ask something that you don't know the answer to. But when you go to do question 7, hopefully you know the flavors in Neapolitan ice cream. If not, then you can look that up, I guess, on the internet or just look at my answer. My question 8 wants me to create a set B. So I'm going to write B equals, and I'm going to do squiggly brackets or set braces, and my set's the day of the week. It doesn't matter the order that I write these in, so I'm going to just do Sunday, Monday, Tuesday, and then I don't feel like writing out the words. I'm going to start abbreviating Wednesday, Thursday, Friday, and Saturday. And the fact that I abbreviated and didn't even use little periods after the abbreviations doesn't bother me. And I didn't have to write the names of the days in this specific order. I could have did Tuesday, Monday, Wednesday, Thursday, Saturday, Friday, Sunday. The order wasn't important. All right, so that's our first 8 homework problems. I don't know that we're even a quarter of the way through this section, but let's just keep plodding along. So the next concept is on well-defined. It says when we describe a set should be well-defined. And then a set is well-defined if any informed objective person can decide if a given element is in the set or not. So this definition is a bit abstract. Usually a set defined with words such as good, bad, and nice are indicators that a set isn't well defined because those are objective. Different people might think different things are bad, and that's not a constant. So let me do an example to help us understand what well defined is. So let M be the set of months with more than 30 days. Is the set well defined? This should absolutely be well defined because anybody that could go to a calendar and look and see, well, January has 31 days, December has 31 days, that's more than 30 days. Those sets belong in the set M. February has 28 or 29 days, that's not more than 30 days. April has 30 days, that doesn't belong in the set, that's not more than 30 days. It's a very well-defined description of our set, so anybody that understood what more than 30 meant should be able to figure out if a month belongs in the set or not. And my answer, is the set well defined? I'm just going to write the word yes, meaning yes, the set is well defined. So it's not ambiguous. Whether a number belongs to a set or not. And I have actually even wrote the elements of the set down. I didn't give it a set name, so I didn't really write it as a set. I didn't use set braces, but those are the elements of that set. And now the next example I have has this key word that tells me a set's probably not well defined. Let C be the set of good cell phones. I used to have an iPhone, now I have a Galaxy, and I think those are both good cell phones. Maybe, there's a lot of people that use iPhones that would say the Galaxy is not a good cell phone, and whatever other cell phone becomes popular or unpopular as I do this video, whether a cell phone is good or not is objective. For that matter, maybe the iPhone 7 or the iPhone, you think the iPhone 7 is good, but you thought the iPhone 4 wasn't good. So it's very objective. Two different people, if you gave them the same cell phone, they might think, one person might think it's good, the other person might think it's not good. Because the word good in there is kind of subjective, this is not a well-defined set, because the answer to whether a cell phone is good or not likely depends on the person who's asked. So this is not a well-defined set. So as we go through the next group of homework problems, we have to look at the problems, and we're either going to say yes, the set is well defined, or no, the set is not well defined. So the instructions say which of the sets are well defined. Write yes if the set is well defined, no if it's not well defined. So my problem 10, B is a set of GCC students whose GPA is 3.0 or greater. That's clearly well defined. I could, ask a student what their GPA is, and if it's 3.0 or higher, they're part of the set. If it's not, if it's 2.9999, if it's less than 3, they're not in the set. This is definitely well defined. Your problem 9, hopefully that's obviously going to be a no. It's not well defined because goofy, again, that's a subjective term. So 11 and 12 are our problems. 11, the set of numbers whose square is 16. 5's not in that set because 5 squared isn't 16. 4 is in that set because 4 squared is 16. You have to decide whether that's well defined or not. 12, the set of good students at GCC. Again, good is a very subjective term. I'm going to write no for the answer there. That's not well defined. I have 13 and 14. 13, the set of years that the Cardinals won their division. 14, the set of Great Lakes. I'm going to say 14 is definitely well defined. Huron, Michigan, Superior, Erie, and Ontario, I think, are the 5 Great Lakes. This is a well-defined set because we know whether a lake's part of the Great Lakes or not. Similarly, you have to decide if the set of years that the Arizona Cardinals have won their division is well-defined or not. Last 2 problems for this group of problems. We have to decide either yes, it's well-defined, or no, it's not well-defined. Mine is a set of good smartphones. That seems like a horrible grammatical sentence. Again, that's objective. And then similarly, the set of cities that have nice climates, you have to decide if that's a well-defined set of cities or if it's objective. So on to our next little bit of theory, and then we'll do some problems to match up with that theory. So sets can be finite and they can be infinite. A set is finite if it's possible, given enough time to write down every element in the set. The set of cars that I've owned, maybe I've owned maybe 10 or 12 cars in my life, that's a finite set. I can list down every car I've ever owned. The set of students in our class, that's a finite set. I can list every student's name in our class. An infinite set is a set that's not finite, which means it's impossible, regardless of how much time, to write down every element of the set. And usually, integers would be considered an infinite set. You can never write down all the integers. If you started writing down the numbers to 1 to a trillion, there's still going to be more integers. You can always add 1 to the next number, and you're going to get a bigger integer. So finite sets are just, infinite sets aren't finite. So here's an example to illustrate these concepts. Here is the set A that has the numbers 1, 2, 3, ... 20. This means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all the way up to 20, and it stops. This is a finite set because if I was patient enough, I can list down all the numbers between 1 to 20, because it's possible to write all the numbers of set A down A is considered a finite set. These dot dot dots are called ellipses, and it means continue with that pattern. Usually I need at least 3 numbers in a row before I can put a dot 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 to establish a pattern. Here's another set. You notice I called sets A all the time. With lack of a better name, I call most sets A. Oh, this is the same set. So this is the set A. It's a finite set because I was able to list all the elements of the set. On the next page, I give you set B. It says 1, 2, 3, dot, dot, dot. Is B finite or infinite? It's impossible to list all the elements of B. I can start writing what these dot, dot, dots mean, but that dot, 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 because that dot, dot, dot doesn't have a number capped at the end. Here is the numbers 1, 2, 3, dot, 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 stop at 20. Here, B is the set 1, 2, 3, dot, 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 don't ever stop. This is a finite set because I'm only considering the numbers from 1 to 20 and I'm stopping at 20. This is an infinite set because I'm considering every number that's in this pattern that's bigger than 3 with no stop. So I started typing these up to the point where I got tired of typing, but I wasn't done writing set B because this is supposed to go on forever without stopping. So no matter how much I write, there's still more of B. So B is an infinite set. Sets are either finite or infinite, and that's an infinite set. All right, another example. Determine whether the set is infinite or finite. The set A contains the factors of 10. Of course, if you don't know what it means to be a factor of 10, this is a hard question to answer. So we need to know what it means to be a factor of 10. Factors are numbers that divide evenly into a number. So I wrote down the factors of 10. 10 divided by 1 is 10, so 1 is a factor of 10. 10 divided by 2 is 5, so 2 is a factor of 10. These are all the factors of 10. Any other number that you might write, whether it's a fraction or it's a decimal, if you take 10 and divide it by that number, you're going to get, you're not going to get an integer. It won't divide evenly. You're going to have a remainder. So these are all the factors of 10. So these are all the elements in the set that's described. There's only 8 of them. So this is a finite set. I don't think ever on a test I use the word factor. I just use it in the example, but it's not, it's not a test-worthy type thing. The next example is going to use the word multiples. And multiples and factors feel similar, but they're different. Factors are any numbers that divide evenly into that number. They can be positive or negative. Next example, determine whether the set is infinite or finite, the set of multiples of 4. Same deal here. In order to assess whether this has infinitely many numbers in it or finitely many numbers in it, we need to know what it means to be a multiple of 4. To be a multiple of 4, that's any number that divides evenly into 4, or any number 4 times any integer gives a multiple of 4. I listed some of the multiples of 4 here. 4 times 1 is 4, 4 times 2 is 8, 4 times 3 is 12, 4 times 4 is 16, 4 times 5 is 20. I could have continued this list. 4 times 6 is 24, 4 times 7 is 28, 4 times 8 is 32, 4 times 9 is 36. Multiples go on forever. Factors are a finite set, but multiples, you could take the number that you're finding the multiples for and you can multiply it by any integer and you get a multiple. So it's impossible to list all the multiples of 4, so this is an infinite set. Homework problems. So I don't really have to list the elements of the set. I just need to determine whether they're finite or infinite. My answers are either going to be finite or infinite. Factors are generally finite. The factors of 24, 1 goes evenly into 24, 2 goes evenly into 24, 3 goes evenly into 24, 4 does, 6 does, 8 does, and 12 does, along with -1, -2, -3, -4, -6, -8, and -12. Oh, and I guess 24 goes evenly into 24 as well. I can't think of any other number that's a factor of 24. All of these, if you take 24 divided by these numbers, you get an integer, you don't get a remainder. This is a finite set. The set of factors is generally always a finite set. I can't think of a time where it wouldn't be a finite set. For 19 and 20, we're dealing with multiples. The set of multiples of 5, 5 times 1 is 5, 5 times 2 is 10, 5 times 3 is 15, 5 times 4 is 20. This list would go on forever because I can multiply 5 by any of the infinitely many integers to get a multiple of 5. So this is going to be an infinite set. I don't really like question 21. How about the set of positive multiples of 4 that are less than 30? Let me change your 21 to that, and let me do your problem 21 as opposed to my 22, because I didn't like problem 21. So if I think of the positive multiples of 4, 4 times 1 is 4, 4 times 2 is 8, 4 times 3 is 12, 16, 20, 24, 28, 32, 36, dot, dot, dot. Those are the positive multiples of 4. In this set, I'm only considering the positive multiples of 4 that are less than 30. So all the numbers that are bigger than 30, which includes all these infinitely many after the dot, dot, dots, aren't part of the set. These are the numbers that are parts of the set. That's a finite set. There's only, 7 numbers there? So your answer to number 21 is that this is going to be a finite set. Similarly, my problem 22 is also going to be a finite set. I'd only include the multiples of 4 that are greater than 10 and less than 50. Because I don't have the or equal to, I wouldn't include the 10 and wouldn't include the 50 if they were multiples of 4. But this is also going to be a finite set. (24) wants me to do the set of odd positive integers, and that's going to have numbers like 1, 3, 5, 7, 9. Those are all odd integers. If I wanted to do it nice, I'd put it in set braces and give it a name, but I don't need to do that to answer the question. My answer to this question is either going to be finite or infinite, and no matter how many odd integers I write, I can add 2 and I'd get to another odd integer. This is clearly an infinite set because it goes on forever. Just add 2 to the previous number, you'll get another number in the set. New concept. The empty set is something that we'll talk to from time to time. I'll almost always call it the empty set. Some older teachers will call it the null set. And the empty set, I like this notation better. Having set braces with nothing inside of it, that's a set that doesn't contain any elements. This is the same as when we write a 0 with a line through it. A 0 with a line through it like that is considered a set with no elements. So here's an example of an empty set. The set A of the months of the year where the average high temperature in Phoenix is less than 10 degrees. So I can write set A has no elements in it because obviously there's never a month in Phoenix where the average temperature is less than 10 degrees Fahrenheit. It's always warmer than that here for the average high temperature. So I could say A, the set of months where the average high temperature in Phoenix is less than 10 degrees Fahrenheit, is a set with no elements. But it would be equivalently right to write either of these, saying A is the empty set, or A is the empty set, or A is the empty set. There's no months that belong in that set. There's another bit of notation that comes up for the word element. This symbol right here stands for the word element. And we say an object is an element of a set if it's in a list of the elements of a particular set. So I would read this: 5 is the element of the set A. When I see this right here, that would translate to these words: 5 is an element of the set A. When you see the notation 5 is an element of the set A, it means that, well, 5 will be in the list if you make a list of all the elements of A. This 6 is not an element of A, this symbol, so this is an element, which means it's in the list of elements of that set, and then this is not an element. 6 is not an element of A means 6 is not a, this means if you listed all the elements of A, 6 wouldn't be in that list. So every object is either an element of a set or it's not an element of a set. So now we have some simple true-false questions just to understand this. So I'm giving you a set B. B is the set that contains the numbers 1, 2, 3, 4, and 5. And now I need to look at the statement and see whether this is true or false. The first statement says 1 is an element of the set B. Because in set B the number 1 is in that list, I'm going to say that's a true statement. Because 1 is an element. This is kind of tricky. This says 1 is not an element of set B. Is that true or false? Well, it's false because it's an element. It's either an element or it's not an element. If it's true that it's an element, it's false that it's not an element. Question C says 8 is not an element of set B. And if I look at set B, 8's not in there. So this is a true statement saying 8 is not an element of set B. This statement, is 8 an element of B? I look at set B, it's not in there. That's a false statement because 8 is not in the list of elements of set B. So these statements are true. This statement is true if 1's an element. This statement is true if 8 is not an element. That's why these were true. Natural numbers come up a ton in this chapter. More so than integers. So far we've only really talked about the set of integers, but now we're going to talk about the set of natural numbers. The set of natural numbers is a set you should be familiar with. The set of natural numbers is often assigned the letter n, and it contains integers greater than 0. It's an infinite set, and the set of natural numbers is the set 1, 2, 3, 4, 5, 6, 7, ... It goes on forever. Now, I'm not sure whether I'm supposed to put a comma and then ... or a ... without the comma. I don't care. I don't know that. There's probably a correct way to do it, but it's not important to us. So, next definition. So, natural numbers is just a set that we're going to use a lot in this chapter. The cardinal number of a finite set is the number of elements in that set. The cardinal number of a set is usually given small letter n and then a. Example, find the cardinal number of set A. The cardinal number is the number of elements in this set, and there's 1, 2, 3, 4, 5, 6. So there's 6 elements in set A. So I could say the cardinal number of set A is 6. The question was, find the cardinal number of set A. This would be a perfectly fine answer. If I wrote that down, the cardinal number of set A is 6, that would answer the question perfectly. It actually answered the question with a sentence, and that's kind of nice. Most mathematicians, when there's an opportunity to create a shorthand to replace writing a sentence, they do that. And this right here means exactly the same thing. So somebody that reads mathematics, at least set mathematics, understand that these mean exactly the same thing. So if I'm asking you to find the cardinal number of a set, that's the number of elements in the set, and if the cardinal number of set A is 6, now it's correct. Now these two things mean exactly the same thing. So when I ask you to find the cardinal number of a set, it's sufficient to write your answer in words or using a symbol, or you can be lazy and just write the number. We'll get to that in a second. So here's an example. Find the cardinal number, the number of elements in set A, where A is a natural number is less than 8. In order to answer how many elements are in the set, I need to know what the set contains, and 8 is not an element of the set because the word less than doesn't include the number that's mentioned. If in order for 8 to be included in this set, I'd have to have the word less than or equal to. So 8 is not an element of the set. 8 would have been an element of the set if it said A is a set of natural numbers less than or equal to 8. Because it doesn't have the or equal to, it doesn't include the 8. So this word less than doesn't include the number that's mentioned. A only contains natural numbers. Natural numbers start at 1, they go on forever. The natural numbers less than 8 are the numbers 1 through 7, not including the 8. Now I can answer the problem because I know the elements in set A. The question is how many elements are in set A, not what are the elements of set A. So although set A contains the numbers 1, 2, 3, 4, 5, 6, and 7, that's not what this question is asking. This question says find the number of elements in set A. This is why when I wrote my answer, I said the number of elements in set A, or the cardinal number of set A, is 7. For my answer, I could have said the cardinal number, which is the same as saying the number of elements in a fancy way. So this would be an equivalently good answer. Or if I was lazy, I might just write the number 7. That's probably what I'd be kind of inclined to do. When they ask me to write the number of elements in a set, if I just include the number of elements in that set without any verbiage or symbols before it, I'm okay with that. All right, now we're going to live with doing some homework problems. So let me work on each one of these problems. So the instructions say that find the number of elements in each set. That is, find the cardinal number of each set. So let me figure out what set B is for my problem 26. Set B is a set of natural numbers, even natural numbers. Here's some even natural numbers. Natural numbers start at 1, but even natural numbers start at 2. So here's some even natural numbers. I only want the numbers between 5 and 10 inclusive, and which means I'm going to include any number. I would include 5 and I'd include 10 if they were in the list. The only natural numbers that are between 5 and 10 inclusive are the 8 and the 10. B is a set 8 and 10. Doesn't include 2 and 4 because that's not between 5 and 10. Doesn't include 12 and 14 because that's not between 5 and 10. Includes the 10 because of the word inclusive. My answer to problem 34, the number of elements in set B, the cardinal number in set B is 2. This would be a perfectly fine way to write the answer. If I want to, I can just write the number 2, or I can say the cardinal number of set B is 2. All of those would be perfectly fine answers for that question. Your problem 25 should work very similarly. These all have to be finite sets. You don't talk about cardinal numbers of an infinite set. Let me look at set A. Odd natural numbers greater than 2, less than or equal to 5. Let me write some odd natural numbers down. I don't have to do more than that. I'm going to include the ones that are greater than 2 and less than or equal to 5. Greater than 2 means not to include the 2. I'm not going to include the 1, the 7, and the 9 because they're not between 2 and 5. I wouldn't include the 2, but it's not in this list anyway, so that's not an issue. I have to decide whether to include the 5 or not, and because next to the 5 I have an or equal to, I include the 5. So these are all the numbers between 2 and 5, and I want the numbers bigger than 2, not including 2. 3 is bigger than 2, not including 2. Less than or equal to 5. 5 is equal to 5, so it counts that. So my set A has the numbers 3 and 5 in it. And for my answer, you see these set braces get really bad the quicker I try to write them. My answer, I can just write 2 down, or I can write the cardinal number of set A is 2, or I can write the number of elements in set A is 2. The cardinal number is the same as the number of elements. All of these are equally correct answer. I'd probably, on my key, I'd probably just write that if it was a test question. So you should be able to give 27 a go. 29 and 30 don't talk about even or odd numbers, so I'm talking about all the natural numbers here. So in problem 30, A is a set of natural numbers less than or equal to 5. Natural numbers start at 1. I'm going to stop at 5, and I'm going to include the 5 because of the or equal to. When you go to figure out your elements of your set A, you're not going to include the 9, but you're going to include 1 through 8. My answer to problem 30, the number of elements in set A, there's 5 elements in that set. I could write 5, or I could write 5, or I could write some words. I'm never going to write the words as a choice. Either I'm going to write a shorthand with a symbol, or I'm just going to write the number. 31, 32, 33, and 34 just ask me to find the number of elements in the set. 32 says find the number of elements in set B, where B is A, C, E, O, and V. My answer to 32, I could write 5, or I could say the cardinal number of set B is 5. Or I can say the number of elements in set B is 5. Those all would mean the same thing. Your 31 is basically the same problem. My 34 says find the number of elements in set D, where D is a set that contains the number 0. This is not the empty set. The empty set has 0 elements in it. This is a set with 1 element. It's the element 0. My answer to 34 is going to be 1. And I could say, just write 1, or I could say the number of elements in set B is 1. Those would both be correct answers, and your 33 is similar. Every 24 minutes my video hiccups, so I reach up and I pause it so I can kind of splice them together. I kind of record these in 24-minute segments, and I splice the segments together. We're getting close to the end finally, I think. Yeah, this is the last concept for this section as near as I can tell. Yes. So two sets are equal if they have exactly the same elements. So question, are the sets A and B equal, where A has the elements A, B, C, D, and E, and B has the elements E, D, C, A, and B? If you look at the elements, they have exactly the same. They both have A, they both have B, they both have C, they both have D, and they both have E. They have exactly the same elements. These are equal sets. Here's another set. Are these equal sets? A has the numbers 1, 2, and 3. B has the letters A, B, and C. These aren't equal sets because they don't have exactly the same elements. 1, 2, and 3 is not exactly the same as A, B, and C. They both have 3 elements. That doesn't make them equal. To be equal, you have to have exactly the same elements. Are these sets equal? A has 1, 2, and 3. B has 1, 2, 3, and 4. No, these aren't equals because A doesn't have a 4, which B has. They don't have exactly the same elements. They're not equal. To be equal, you have exactly 100% the same elements. Equivalent is something where the bar is a little bit lower. Finite sets are equivalent if they have the same number of elements. These two sets back here, we'll get to these again, these are an example of equivalent sets. They both have 3 elements. That makes them equivalent but not equal. Let's look at the sets A and B from all the other examples. Are these sets equivalent? Well, they were equal because they both had A, B, C, D, and E in them. They're also equivalent because they have exactly the same number of sets. So these sets are both equal and equivalent. They're equal because they have exactly the same elements. They're equivalent because they have the same number of elements. The question is here, are they equivalent? And my answer was yes, because they both have 5 elements. The next example, these two sets, A and B, both have 3 elements. These are equivalent, but they're not equal. They're equivalent because they both have 3 elements in them. So these sets, they're not equal because they have different elements, but they are equivalent because they both have 3 elements. So you can be equal and equivalent. and you can be equivalent but not be equal. So there are different concepts. Equal is exactly the same. Equivalent's only the same numbers. Obviously, if you're equal, you have to be equivalent, because to be equal, you have exactly the same elements, which means you have exactly the same number of elements. And then the last example, are these two sets equivalent? And the answer would be no, because A has 3 elements and B has 4 elements, and to be equivalent, you have to be both, you have to have the same number of sets. These problems are missed a lot on the tests over Chapter 1. The instructions are determine whether the sets A and B are equal, equivalent, and neither. It should say include all correct choices. So the set A here has 4 elements. The set B has 4 elements. They have the same number of elements, so they're absolutely equivalent. They're not equal because B has an O and an I in it, and A doesn't have that O and an I in it. They don't have exactly the same elements. They're not equal. So the answer to this is these sets are equivalent, and they're not equal. The neither is going to be reserved for sets that aren't equal and aren't equivalent. Here's another example of some sets, A and B. Are these sets equal, equivalent, or neither? When I look at the sets, they both have the letters A, B, C, and D, and they both have 4 letters. Because they both have 4 letters, they're equivalent. Because they have exactly the same 4 letters, they're equal. So when I went to write my answer to this, determine whether they're equal, equivalent, or neither, I included both equal and equivalent. Whereas in this last problem in my answer, I only put equivalent. I didn't include equal because they didn't have exactly the same elements. Here, they both have 4 elements. That makes them equivalent. To be equivalent, you just have the same number of elements. And then they have exactly the same elements, so they're equal. Last example before we get into the homework. Are these two sets A and B equal, equivalent, or neither? They're not equivalent because they don't have the same number of elements. This has 3 elements, that has 4 elements. It makes them not equivalent. And they're not equal because there's a D in set, there's an A in set B that's not in set A. So they don't have exactly the same elements, they're not equal. They don't have the same number of elements, so they're not equivalent. That makes these neither. The rest of the homework problems, we are going to do exactly this. We're going to be given a set A and a set B, and we have to figure out if they're equal, equivalent, or none. So your 35 is a little bit different than my 36, because your 35, when you go to answer this set has 4 elements, that set has 4 elements. Part of your answer is they're going to be equivalent because they both have 4 elements. Now, they both have the only A, B, C, and D. They have exactly the same elements. It makes them equal. For my sets, they're not equivalent because A has 4 elements and B has 3 elements. Makes them not equivalent. And they're not equal because A has a 1 and B doesn't have a 1. The answer to my 36 is going to be neither. Neither. So hopefully you can do your 37. I'll do my 38. Both of these sets have 2 elements. That makes them equivalent. In problem 38, to be equivalent, you just need the same number of elements. They happen to have exactly the same elements, so they're also equal. So these are going to be both equal and equivalent. Then give 37 a go. Now I'll move on to 39 and 40. I'll do my 40. I look at set A, it has 1, 2, 3 elements. I look at my set B, it has 1, 2, 3 elements. That makes these two sets, A and B, absolutely equivalent. They have exactly the same number of elements. That's 3 elements. Now when I look at, for equality, they don't have exactly the same elements, so they're not equal. My answer to 40 is only going to be equivalent. I'm not going to write equal because they don't have the same elements. I write equivalent because they both have 3 elements. Our 41 and 42 is a little bit different. Let me just do 42, 1 instead of 42. So I'll never do 42. When I look at sets A and B here, they both have 2 elements. That's enough to make them equivalent because equivalent sets have the same number of elements. And I have to decide whether they're equal or not. Well, they're not equal because they don't. B has a 4 and A doesn't. A has a 2 and B doesn't. So they're only equivalent and they're not equal. Last three problems. You get 2 and I get 1. My 44, both sets have 5 elements, so they're equivalent because to be equivalent, you have to have the same number of elements. And for equal, they both have 1, 2, 3, 4, and 5. They have exactly the same number of elements, and they have exactly the same elements. So my 44, they're both equivalent and equal. So give 43 and 45 a go, and that will be the end of our first section. Here's the answers, just in case you wanted to go back and check some of your work.